We like to think of the modern world as weightless. We store our lives in the cloud, connect over wireless networks, and interact through glowing, ethereal screens. But that digital utopia is an illusion. Every tap, swipe, and server request is anchored in thousands of tons of physical Earth. For 100 years, global power was built on the continuous combustion of fossil fuels. Today, that power is shifting toward the extraction and refinement of non-combustible metals. The sheer scale of modern mining forced the U.S. government to redefine the bedrock of our civilization. In 2025, the U.S. Geological Survey finalized a list of 60 elements, the 2025 Critical Minerals List, deemed vital to the nation's survival. This flowchart shows the exact methodology used to determine what makes a mineral critical. To make the list, an element must meet a strict legal threshold. It must be essential to the economy or national defense, and its supply chain must be vulnerable to disruption, measured here by the probability of a massive GDP decrease or a single point of failure in domestic processing. The periodic table now serves as a strategic map of geopolitical leverage and national security. The first pillar of this material demand is the physical infrastructure of the energy transition. Building a decarbonized grid requires millions of electric vehicles, sprawling solar arrays, and towering offshore wind turbines. Most of the focus has been on battery chemistry metals, elements like lithium and cobalt. These are the charge carriers and stabilizers that allow engineers to maximize range and energy density when assembling electric vehicle battery packs. But the 2025 Critical List update added a new category of threat: massive, high-volume industrial metals. For the first time, copper and silver were officially designated as national security priorities. Copper is the foundational architect of the electrical grid, irreplaceable for its ability to transmit power with minimal loss. Silver, meanwhile, has become a severe bottleneck for the renewable sector, as it is the primary conductive paste used in nearly all photovoltaic solar cells. The transition to a green economy is physically limited by the raw tonnage of base metals available for extraction. The second pillar is the computational brain of the modern world. The hardware required for artificial intelligence, 5G networks, and quantum computing has moved beyond basic silicon to rely on specialized microscopic metallurgical byproducts. Advanced networks now depend on ultra-rare trace elements like gallium and germanium. These materials are not mined directly. They are recovered as minute byproducts during the processing of aluminum and zinc. Gallium possesses an exceptional ability to handle the extreme heat and massive voltage required by AI data centers and military radar. It is often used to create gallium nitride, a semiconductor compound that vastly outperforms silicon in high-power environments. Germanium is equally vital. It is used to manufacture the ultra-pure, infrared-transparent fiber optic glass that forms the physical backbone of the global internet, allowing data to travel thousands of miles across the ocean floor. The potential of artificial intelligence is hard-capped by the geological scarcity of these microscopic trace elements. The final pillar is the advanced defense shield. Maintaining military supremacy requires a constant supply of materials for hypersonic glide vehicles, nuclear-powered submarines, and fifth-generation tactical aircraft. Precision-guided munitions rely on high-strength permanent magnets made from rare earth elements. Specifically, neodymium is used to forge magnets that allow electromagnetic actuators to maneuver missile flight surfaces with absolute precision at supersonic speeds. For hypersonic weapons, traveling at 5 times the speed of sound, atmospheric friction generates temperatures exceeding 2,000 degrees Fahrenheit. Refractory metals like rhenium and titanium are the only materials capable of surviving these extreme thermal loads without melting. The 2025 list also reinstated uranium, recognizing its dual role as the zero-carbon baseload power for our grid and the ultimate nuclear deterrent for our defense. Supremacy in the modern theater of war is won in the laboratory and the refinery through a high-stakes material science arms race. There is a structural weakness in this entire system. Having raw critical minerals in your domestic soil is irrelevant if you lack the industrial capacity to chemically refine them. This chart compares global market share for raw extraction against downstream refining, proving China's extreme monopoly over midstream processing. The disparities are stark. China controls 99% of graphite refining, 95% of gallium, and 91% of rare earths. This concentration creates a systemic single point of failure. It allows foreign adversaries to weaponize supply chains through export controls, potentially crippling rival technological and defense sectors overnight. To counter this, Western governments are injecting billions of dollars into aggressive domestic industrial policies. The goal is to build a midstream processing base that bypasses these foreign monopolies entirely. This tree map chart breaks down the federal capital deployments of the U.S. bipartisan infrastructure law. It emphasizes massive allocations dedicated to battery materials processing and advanced manufacturing grants. These policies are also driving a push for urban mining, recycling end-of-life electronics and batteries to reclaim their base elements. At the same time, new projects are working to isolate rare earth elements from legacy coal waste and mine tailings. These initiatives are designed to achieve total supply chain decoupling, ensuring that the materials required for national security are sourced and refined within the U.S. or through allied nations. Global supremacy in the 21st century belongs exclusively to whoever masters the chemistry, extraction, and refinement of these 60 invisible elements.